And so one example would be this function that's shown here, which is just a sine function. So we've got the function theta equals theta. And so within a certain, we can approximate the sine function by a linear, by a line, I guess. But that line is only good within a certain range. So really, we know that the slope of a line is the derivative of the function. So here, so the slope of the line is the derivative of the function, and in this case, the slope of the line is going to be the cosine of theta. So down here in the range of, if we look at 0, the slope of the line is going to be the cosine of 0, which is equal to 1. So we end up with a line that has a slope of 1. And within the range right around 0, this is a reasonable approximation. But once we start getting, too far away from 0, it just really is a poor representation of the function. And likewise, we end up here, I believe this is at pi over 3. And then this one here is at 2 pi over 3. And so right around that that point, the slope of the line there is reasonable. So that's one way of linearizing data and going about it. A more kind of robust way of looking at that, though, is probably looking at an analytical method like the Taylor series function, which we'll get to on the next slide. So what I've shown on the slide here is the Taylor series, which is probably some kind of foggy memory from one of your calculus classes. But basically, all a Taylor series is a representation of a function, and it's a series that's based on the derivatives of that function. And we generally can use that if we're staying fairly close to the reference point. So for what we're showing here, we're calling this theta r. If we stay fairly close to that reference point, we can approximate the function using just the first two terms. And so that's what I've shown right here. We can drop off these higher order terms of the Taylor series. And the reason we can do that is if theta is reasonably close to theta r, then this, as soon as we start making this squared or cubed or all the way up to this, to the k power, this term becomes so small that these terms become insignificant compared to the first two. So in general, for most of our applications, we can just take these higher order terms and neglect them because of the fact that we're talking about the function close to that reference point. So although this, once we truncate it, it's certainly a lot less intimidating than the first equation that we had here. But if we look at this, it really is just a linear function. So if we took this this function evaluated at the reference and moved it over to the left-hand side of the equation and got f of theta, sorry, that's supposed to be a minus, not an equals, f of theta r. Just move that over there, and then that was supposed to be an equals. I'm really having a hard time here. And this is the derivative of the function at theta r. And I'm sure those aren't going to show up on YouTube, but that's okay. All I'm saying is that evaluating it at theta equals theta r, and then multiply it times theta minus theta r. So if we put it into this format, this here part can become our y. The derivative becomes our slope, which kind of makes sense. And the x term becomes the difference between of how far the theta that we're trying to evaluate compared to the reference point. So we end up with this y equals mx plus b. And and using these coordinates and showing your equation just as y equals mx plus b, instead of worrying about this the derivative, it could just kind of simplifies things and makes it a little less intimidating to try to go about solving. The last example I've got for this little section is showing the linearization of a square root model, and I took this example as well from the textbook so you can follow along, but basically as we start developing these models, if we're developing them from fundamental principles, they often end up having nonlinear components associated with them. The previous example with the sine function is common, but probably more common than most is finding something that has a square root. So having something where f equals the square root of h is quite common, and obviously dealing with a square root and trying to solve things or predict values and come up with a model, it's not exactly trivial to work with that. However, if we use the Taylor series to expand this function out within a range, within a range around a certain point, we can get a reasonably good approximation, and that's really what this question is asking you to do. So I'm going to go ahead and start writing some of that out instead of just sitting here letting you listen to me breathe. And this might be a good point for you to pause it, and based on what I showed you on the previous page, maybe you could try to solve this on your own and then play it and see how you did. So I'm going to go ahead and pause, and I would suggest that you do the same. So all I've done here is solve through, or I've written out the general form for the Taylor series, just showing the first two terms because we're assuming that we're only near this point, h equals 9. So if we set the reference equal to 9, we can substitute in, and we would get this line right here. And then all I'm doing is substituting or calculating out and solving this part for this part here for 9. And we end up with this 3 plus 1/6 times h minus 9. And what this equation here that I've got, this f of h, corresponds to the slope, or to the line, sorry, the equation that represents this line right here, which is the slope at the point 9. So when we go through and get this, it's not it's not the slope, it's the Taylor series approximation of this line right here. So if we had chosen to, if I'd ask you to come up with a linear approximation that was valid near, let's say, the point 25, what I would be asking you for is a line that approximates, right about there. And we would have just went through and evaluated this at HR is equal to 25 instead of calculating it at 9. So that's the Taylor series approximation. I would suggest that you go back and just take a look at that and make sure you're comfortable with that math of going through the Taylor series. It's likely in Math 415 that you would have had to, derive things and try to prove various things. The purpose of this, using this in an engineering application, is to shorten the amount of time that you have to spend doing something. So what I would just suggest you do is make sure you've practiced using it, and make sure you understand why you use a Taylor series, and the rest of the details of Math 415 you can kind of leave behind you, I think. So if you have any questions, please feel free to post them on the Carmen site, or give me a call or send me a text message or whatever. So I'm going to sign off from here, and our next, I will have the next one up at some point tomorrow, and we'll be talking about identifying functions and estimating various parameters, and that kind of gets us into the idea of using MATLAB to solve some of these problems, which should be helpful for you. So I'll stop rambling. Have a good night. I'll talk to you soon. Bye.